Hello, everyone. Welcome to my talk on hardware acceleration for FHEW. In this talk, I'd like to talk about, well, two things. One, about hardware acceleration in general. And secondly, about my master thesis, which was doing a hardware accelerator for FHEW. But before we get started, for all the people here who are not really into hardware acceleration, let's give an introduction to hardware acceleration. So what is hardware acceleration? Well, hardware acceleration is trying to speed up some sort of computation task with hardware. And the best way I can explain this is by thinking about a factory, which is trying to produce things. Now, you can do this in multiple ways. You can hire some humans, tell the humans, I want this thing produced, and the humans will hopefully get to work. And there are multiple advantages of this. Humans are very good at understanding instructions. They are relatively cheap and they are flexible. If one day you decide you no longer want product A to be produced, you can switch to humans easily over by saying, now I want this produced. And so it is with CPUs. CPUs are relatively easy to program. They are cheap to reprogram. They can be reprogrammed quickly. They are very flexible. But, and this is also one advantage with humans, if you want really a lot of things produced, if you want really a lot of throughput, humans and CPUs are not that great. If you want, in the case of CPUs, GPUs, FPGAs, and ASICs, if you want a lot of data processed, you are going to tend more towards the right side of this graph, towards the FPGAs, towards the ASICs, which are like robots. They can only do one thing, but that one thing they do really well, really efficiently, and they can produce a lot of things very, very quickly. And this is, but there's of course disadvantages with this. In the case of on a factory floor, once you have a robot producing cars, you will not get it to produce pencils without either switching out the robot for a new robot or by completely reprogramming what the robot can do. So the things on the right side of this graph, the FPGAs, the ASICs, once you program them, you've done this for one task. That one task will be really efficient. Everything else will be not so efficient. And so given this, like, how does an FPGA do this? What is really the trick of an FPGA? Well, an FPGA can be seen as a tiny circuit connected to a 1-bit memory, and this in a giant array, because an FPGA stands for field programmable gate array, and that array consists of millions of these gates. So this tiny circuit, you can kind of think of it like an AND gate, for example. Like, it's just a very, very simple calculation followed by a 1-bit memory where the value can be temporarily stored. And what you then do is you have interconnect between all these tiny circuits, and that's controlled by the user. So these tiny circuits, they stay on the chip. The 1-bit memories, they are just on the chip. You work with that. But the interconnect, the user can control. And by controlling this interconnect, you control what the FPGA is doing. Now, previously I said that the tiny circuit is like an AND gate, and that's pretty close. The tiny circuit can, for example, be a lookup table. What is a lookup table? Well, a lookup table is basically a circuit that implements a function going from 64 possible inputs to 2 possible outputs. And any function can be implemented with this lookup table. So it just takes in 6 bits, and you can program yourself what output it gives for any of those 6 bits. The tiny circuit can also be something a little bit larger, a digital signal processor, for example, because sometimes in a lot of applications, you want to do some sort of addition or multiplication. And then you're more interested in sort of taking larger inputs than just 6 bits. Then you might take an 18-bit input, 27-bit input, multiply them together, get a 48-bit output out after doing some additions after the multiplication. That's what a digital signal processor does. It's meant because FPGAs are often used for digital signal processing, but it can be used for all sorts of things. You can also use it for cryptography. You use it for anything where you need multiplications and additions. And finally, this tiny circuit can also be can also be a memory, because as you've seen, there's lots of 1-bit memories in that big array, but that doesn't add to a lot of memory at the end. So sometimes you want some bigger memory, like a block RAM or an ultra RAM. These things could store on the order of kilobits, kilobytes, sometimes half a megabyte. Not much, but significantly more than the tiny memories that you saw in the previous slide. And so that's basically what an FPGA is. But an FPGA on its own, as previously mentioned, is not something very flexible. It can do one task, but it requires a lot of effort to do that one task. So you want to combine this FPGA with, for example, CPUs, embedded CPUs into the FPGA, or you want to connect the hardware accelerator board on which you have your FPGA to a CPU. And to get this connection working properly, there are multiple ways of doing it, but if you really need to communicate a lot of data, and this is often the case, you're going to use something called high bandwidth memory, which is a way of storing a lot of data very quickly and transferring it over from the FPGA to the CPU, or from the CPU to the FPGA via this high bandwidth memory. And together, these three elements, along with some other things like network cards, PCIe, they make up a hardware accelerator card. And this hardware accelerator card you can put into your server, and via the HBM, this hardware accelerator card can communicate with the CPU in your server, or it can communicate with a CPU inside the FPGA. But together, these things communicate. Together, these things can work flexibly and efficiently. You do the CPU for all the flexible things. You do the FPGA for all the high throughput things. You get the best of both worlds. Okay, now you are all FPGA experts. We can continue on to FHEW. So what is FHEW? Now, for a lot of you, FHEW is a cryptographic algorithm based on RGSW ciphertext and RLWE ciphertext. But for a simple hardware designer like me, I look at the FHEW algorithm and I scream and panic, and then I look at the for loops that make up that algorithm, and then I calm down because I can see, like inside these for loops, the following pattern emerge. What you do in the FHEW algorithm, from my perspective, is you do an inverse entity, a signed digit decompose, 4 entities, 4 multiplications with some bootstrapping key, and then you sum these together, and then you go back and you do this over and over and over again in the FHEW algorithm. And you do this a whole bunch of times, which is really good for FPGAs, because this is what you want to do in an FPGA. You want to do one task and you want to do it efficiently, because then you minimize the amount of stuff you have to program. And FPGAs are very good at doing one task in parallel, or doing one task a whole bunch of times very quickly. The second thing a hardware designer then looks at is, okay, these are the things that we should do. Which of these things are the most crucial? Which of these things take up the most space to do? Well, the multiplication here is a pointwise multiplication, just like the addition, which is a pointwise addition. So that's going to take a maximum of n. In this case, the dimension is 1024. So it's going to take 1024 multiplications per multiplication block and 1024 additions per addition block. On the other hand, the number theoretic transform is going to take n log n operations. It's going to take 1024 times 10 operations. These operations are a combination of multiplications and additions, but the point is the entity here is really the big block, as is the inverse entity. These are the blocks that are, in terms of area, much more important. These are the things that we should focus on. The signed digit decompose is just a way of breaking down a number into its own base, in the same way that, for example, you can turn 512 in base 10, that will be 5, 1, and 2. So this is just a series of additions and if statements. It's not that expensive. So really the thing we should really focus on in this hardware acceleration from a hardware perspective is number theoretic transforms, inverse number theoretic transforms. And so that's what we did. Now, there's no point in reinventing the wheel. Entity designs already exist. And we did a study of a whole bunch of entity designs. And after a while, we found this one, Merz and his team. Merz is in the chat, by the way. I just saw him. So if he has some questions, he should definitely ask. Or if you have some questions about his specific design, you can ask me, or you can ask him, because he's the original source. And so his design is in 2021 was definitely the best open source and even non-open source entity design out there. It really reaches the best figure of merit. The best figure of merit being, like, for a given amount of area, how much throughput do you get? Well, this is the best you can get. And it's also very modular, you can, it consists of a whole bunch of processing elements in parallel. Each of these processing elements is sort of like a butterfly. And a number theoretic transform, for those not in the know, is like a fast Fourier transform. It is built up of butterfly elements. And each butterfly element looks approximately like the figure you see here. And by having a bunch of these processing elements which mirror these butterfly elements in parallel, you can go pretty quickly through a number theoretic transform. There is only one problem, which I will come back to. It's a very modular design, so it's easy to scale up, but it was really designed for lattice-based cryptography, like Kyber, Saber, and not really for fully homomorphic encryption, but I will come back to this. So what is then the design that we end up building? Well, we want to mirror our FHEW design. We want the most efficient. There's one task we have to do, namely do the inverse NTT, do the signed digit decompose, do the NTT, and a multiply accumulate at the end. And so each of these entities is made up of a whole bunch of these processing elements that we took from Merz open source design, combined into one whole that we programmed ourselves. So this was sort of the plan to do, but we ran into two problems. We ran into a problem that's related to the FHEW scheme itself, which is going to be interesting for the cryptographers here. And we ran into a hardware problem, that the entity was too small for small chips, which will be interesting for the hardware designers here. So first, the scheme problem. The bootstrapping key is too large. The bootstrapping key on FHEW is just way too large. There were several inputs for FHEW. You have an accumulator, which is sort of your normal input. It consists of two vectors of size 1024. That's no problem for loading in. It also has a vector A, which is a vector of 512 values, which indexes the bootstrapping key and also affects the control flow of any FHEW scheme. And finally, you have the bootstrapping key. And the bootstrapping key is 1.3 gigabytes. It's because of all these for loops coming together to form this many values. And 1.3 gigabytes is really a lot, because the FPGA itself, if you take all the DRAMs and URAMs and registers together, gives you about 40 megabytes. And 40 megabytes is much smaller than 1.3 gigabytes. And this is a problem. Like if it almost exceeded the FPGA, we could work around this in various ways, but because it significantly exceeds the space on the FPGA, there's no way on working around this. You just have to accept that you cannot store any part of the bootstrapping key onto the FPGA except very briefly. And so we must use high bandwidth memory. High bandwidth memory can store up to 8 gigabytes, and it can process data from the high bandwidth memory to the FPGA at 460 gigabytes per second. This in turn means that we're going to have to be careful with using the HBM, because 460 gigabytes per second is not that fast when you have to deal with 1.3 gigabytes. Now, the problem is that programming HBM is not very easy. So this is a direct result of working with a 1.3 gigabyte bootstrapping key. We have to work with HBM, but HBM is not easy. So like creating the data path that you saw previously took 3 months. Making the HBM interface work took 6 months and is still kind of ongoing. We're almost done with that, but it is a significant task. And the reasons for this is not that it just requires some experience with HBM, but simply that the HBM interface must be very efficient. As previously mentioned, 460 gigabytes per second, it's not that fast when you have to process 1.3 gigabytes. So you really need to get that best case throughput, and 460 gigabytes per second is the number that the manufacturer gives, but you will only get that in like absolutely ideal circumstances. In normal circumstances, you will not get that. And you will especially not get that if you're going to have to index which blocks you pick for the HBM interface. Then you're going to have to be very careful with how you design it. You're going to have to be very careful not to disrupt the bursts from the HBM interface. So a naive HBM interface will cause you to become memory bound. It will make the interfacing from the HBM to your data path the rate limiting step. That will be your bottleneck. So to avoid that, you have to design an efficient HBM interface, which is why it takes so long. But there is hope on the horizon. Very recently, I saw a very nice preprint on on the ePrint called Efficient FHEW Bootstrapping with Small Evaluation Keys. And this is, I mean, our design is of course built for an older version of FHEW. It's built for the version of FHEW that was at that moment being run on Palisade. So for that one, it works. But this paper offers perspectives for an even better design than mine, because it is able to get its keys down to a key size of only 12 megabytes. And 12 megabytes is smaller than the 40 megabytes that fit on an FPGA. So with a design like this, with a scheme like this, it really is possible to just, for FHEW, not just for TFHE, but for FHEW, have the entire bootstrapping key on the FPGA. You do not have to deal with HBM. And that makes, of course, designing such a hardware accelerator much easier. So for newer versions of FHEW, this is not a problem anymore. For older versions of FHEW, you are stuck. And for larger schemes, you are stuck with the HBM. The second problem is a hardware problem. So as previously mentioned, we are targeting very high throughput on big chips, while Merz design kind of worked for post-quantum entities, and it sort of assumes small chips, or it assumes that you're going to do a lot of work for every entity. And that causes some problems, because if you assume that you are going to be doing a lot of work for every entity, or if you assume that you're going to have very few processing elements, then you can make assumptions such as, I'm going to read out data out of my entity processor one by one. And then now I'm going to have to indulge in like a thought experiment here. Like, imagine that you're building a giant factory, but your entry gate is very small. If your entry gate is very small, you might be able to process everything very quickly. You might be able to, as soon as trucks arrive, like empty them, but you can only process one truck at a time. And that's sort of the problem with Merz et al.'s design if you use a lot of processing elements. Like, you can feed in the data in about 1,000 cycles. And if you spend 10,000 cycles doing your number theoretic transform, that's no problem, because I mean, it's only a 10% overhead. But if you spend 1,000 cycles reading in your data, and then you only spend 250 cycles processing on it, well, now you've spent 4 times as long on just loading in data than you spend on actually doing the calculation, which is a waste of time. Now you can improve this by pipelining or by trying to work around this, but the best thing to do is to just increase the throughput that can be fed into Merz et al. And that's what we did. We massively increased the amount of data that can be loaded in every cycle. But this brings its own problems, because now, since you're loading in data in parallel, you have to keep track of where it is stored, and you have to make sure it is permuted properly so that you're not loading in the wrong data at the wrong time. So finally, our results. We are almost there on hardware acceleration, so we'll soon have real results. But for now, in simulation, our hardware takes 17 milliseconds, while the software takes 137 milliseconds. I should note that these results are for 100 megahertz of frequency. We know that our entities can run at 200 megahertz, and the rest of our circuit can also probably run at 200 megahertz. So this can probably be improved. But there are other ways that we can improve this design. Namely, first of all, as previously mentioned, there are now few schemes that do not rely on high bandwidth memory, which is very nice. So any future endeavor to hardware accelerate FHEW should definitely use that. And secondly, we can build much better entities now from what we have learned from Merz et al. Merz et al.'s design has certain interesting properties that allow it to be very flexible. But for fully homomorphic encryption, you don't quite need that flexibility, especially not for the 3rd generation schemes. So you can significantly improve the throughput per area over even the best entity design, which is what Merz et al.'s design was in 2021. So there's still a lot of improvement possible. Thank you for listening. And I really hope you have questions, because I am very willing to go into detail on any of this.
Okay, thank you very much, Jonas. Do we have any questions? Don't be shy.
Please don't be shy. Yes.
Should we raise our hand or no? We can go. Apparently.
Just go. Nobody's
Right.
talking. That's their problem.
Cool. Thanks, Jonas. Great presentation. I have a couple of questions. Yeah, on this slide. So you have better entities coming. That's for another publication, or is
that's
that
for another publication? Yes.
Okay.
I don't want to give too much away for that.
When can we expect that one?
The entities are ready, but we're still sort of working with different schemes and seeing which scheme we can really accelerate the fastest.
Okay, I see.
I'm working with Hilder on that, and with a master's thesis student, but we'll we're not quite there yet on the scheme itself. We have the entity, but not the scheme. Okay,
I see. You're familiar with the Z Prize that happened last year, of course.
Yes.
Like there's, I think, 5 entities or so now in the open. You mentioned a clock frequency of 200 megahertz. Do you think you can boost that up using, for example, well, I mean, the supranationals submission reaches like clock frequencies over 400 megahertz. Do you think if you base your new entities of those components that you could go a lot faster, or you would get into problems with the HBM again?
No, you can definitely, based on supranationals design, based on our design for Z Prize, the one that we're currently using for our next paper is based on our Z Prize design scaled down for final parameters. So we can definitely improve a lot on this using those entities. This was, there's, like you said, the Z Prize gave us opportunity to really work on entities. Also, the Z Prize, the final choice in Z Prize, because Z Prize, for the people who don't know, that was the entity task was building an entity of ring size 2 to the power of 24. So that's very large. That's 16,770,000 something. So that's much larger than this, which is on a ring size of 1024. Most third generation schemes are like ring sizes 1024. So the Z Prize had its own issue that their HBM managed a lot, because that was memory bound. Like you could, even with a not very efficient entity design, you could beat Z Prize as long as you had a very efficient memory design. The memory design there was really very important.
And then a final question related to that: are you in your submission with Z Prize, you used HLS, right?
Yes, our final.
Is that, is that still something you use like regularly, or you transfer? Like, do you use mixed designs? Like, do you stay only in high level synthesis? What's your approach there?
My approach is Verilog and really low level design. But we do Michiel does a lot of HLS. At Z Prize was really Michiel. And we're also trying to combine it, get the best of both, because really for HBM, you sort of want to use HLS, so you don't have to deal with all the issues. But for your entity designs, for like the things that will actually determine your area, you would like to use RTL, of course. And go
ahead.
And the problem is that there's not a very easy way. Like Xilinx doesn't provide a very easy way to use both at the same time. At least not yet.
I see. Yeah.
So
related to that, how much of the HBM, like how well documented is it, or is it a lot of like trial and error, a lot of figuring out things?
You should ask Furkan for that, because Furkan also helped me a lot with my HBM design. He is really the expert on this. But from what I hear from him, it's a lot of trial and error. Yes, it's not that well documented.
No surprise.
And I'm also struggling with it. Like I also went through this. But Furkan is really the expert. Furkan knows much.
Cool. Thanks. I might have more questions later on. We'll see. I might not. Looking forward to the paper. Good luck submitting that and getting it accepted at a nice conference.
Yeah, this one I got submitted and accepted at.
This one, but the entity one as well.
Thank you. Okay, so for Anders, what is the drawback of GPUs versus FPGA in an FHE context? So I will go back to my first slide. So I would say in an FHE context, you can do very like the nice thing, of course, of a GPU is that it's easier to program, and you already have nice, like you don't have to worry about things like HBM because that's baked into the GPU, of course. So like in terms of the memory that you have to load in for the GPU, in terms of like if your FHE scheme, and I'm assuming like this is a question for both second and third generation schemes, but I'll start with third generation schemes. For most third generation schemes, except for a few, you don't have that much memory. But for few, you do need to load in a lot of memory, and so GPUs are nice for starters because you don't have to deal with HBM in GPUs. Like it's like you're loading in a lot of data when you're doing graphics. So I mean, it sort of comes with the GPU. This is also why you use GPUs for all those other applications. But of course, the drawback is that once you have your HBM programming issues solved, it's going to be hard for a GPU to beat an FPGA, because an FPGA can have only the data path that you need strictly for an entity, while a GPU is always going to have useless logic on the FPGA, on the GPU. There's always going to be circuits on the GPU that you are not using for your number theoretic transform, because a GPU is not a circuit solely dedicated to doing number theoretic transforms. It's a circuit dedicated to doing a lot of operations. I think often, but I'm not a GPU expert by any means, I think often a lot of floating point operations. So like an FPGA will be the GPU once you have put in all the effort of optimizing it. That's basically the answer. Then new question. What about Intel HEXL? What's the difference between AVX acceleration and FPGA acceleration? So again, I'm definitely not an expert on AVX acceleration. Yeah, I think, no, actually I haven't studied it, so I'm not gonna, sorry, I can't really answer that question because I don't know Intel Hexel. So I know what AVX is, but I don't know Intel Hexel. So
okay,
I would prefer not to answer that question if that's okay.
Sure. Any further questions for Jonas? Pascal?
Yeah, hi, Jonas. Thank you very much for the very nice presentation and for all your work. I was wondering, because, you know, FHE is not like usual crypto where you can use a fixed set of parameters. They're like very often you want to optimize the parameters for a certain evaluation because you kind of figured out how to optimize the parameters for a given circuit or for a given like a program evaluation. And so what is the degree of flexibility towards parameters? Because there are many of them, right? So typically, what are the parameters that are that in your design, in your approach, should not be seen as degrees of freedom, like the ones that are the most fixed or that you can change, but a change could have like drastic, consequences. And because I assume some other parameters on the opposite side could be seen as like completely flexible. Like you would pick whatever number. You can even pick that parameter from the software side when you call the FPGA. But I guess like, because there are like a dozen, maybe 15 parameters, depending on how you view things, I guess they do not all are in the same bag, right? So how did you treat them? What is the granularity of these parameters? What is fixed and not that easy to change in your design approach?
Yeah, so there's definitely like two levels of flexibility here. You have the flexibility of I can change this in like a day by reprogramming something, and you have the flexibility of like I can change this from software. Yeah. And for your first question, like which parameters should be definitely fixed, like from the get-go. I would say like as many as possible, as many as you can get away with fixing beforehand. That's good, especially for hardware design. Like in my specific approach for this master thesis, because I was using Merz design, the modulus is flexible, can be changed in a day. The ring size is even flexible, can be changed in a day. The twiddle factors are, of course, almost always like at least in this case, they are flexible. They can also be changed they can be changed even faster. They're not changeable from software, but they're pre-computed. It's changing a text file. So these things can be changed relatively quickly and don't have that much of an impact. But it's better for the hardware designer. It's better for efficiency if these things are fixed. If you make sure that these things are fixed, the hardware designer can really optimize for specific parameters, especially the modulus. It is highly recommended that you fix that and you fix it to something efficient. This is also starting to creep towards my next paper, so I have to be silent here.
Okay, thanks.
Yep, so there's a couple more questions in the chat. So Riyadh asks, have you considered using CGRA instead of FPGA?
I'm sorry, but I don't know what CGRA is.
Okay.
I'm sorry.
Yeah, maybe one we can follow up with on the Discord server, perhaps.
Yes.
And then
I will first have to look up what CGRA is.
Sure.
Okay, how much of the U280 resources did we use and did your custom? So I originally built my master thesis for a ZUC 102, and it barely didn't. It kind of used the resources of a ZUC 102 exactly, which meant it didn't fit, because if you use the resources exactly of an FPGA, it means you don't fit. So I think about 250,000 LUTs off the top of my head. It's also in the paper, but off the top of my head, 250,000 LUTs, which is about 1/4 of a U280. So of the final design I'm targeting, it will take up about 1/4. And all the things other than LUTs were smaller percentage-wise. Like BRAMs was like 10%, DSPs was like 6%. So 1/4 of a U280. I did not use custom floor planning because it is small enough. I am running it at 100 megahertz. Probably the SLR, I haven't really done enough testing yet to see, like, once I increase the frequency, how that's going to affect it. Probably it will affect it. So I will probably struggle to actually reach 200 megahertz because of this. But I haven't tested that specific part enough yet. I know it from my other designs. When we did the Z-Price design, yes, we were struggling with SLR crossings, but you can, like, at 100 megahertz or at 200 megahertz, it's not as much of a struggle as for higher frequencies. It's also going to be a bit more of a struggle, specifically because the way that, for people who don't know what SLRs are, basically the FPGA, Xilinx creates its bigger FPGAs basically by stacking multiple smaller FPGAs together, and then having these things called SLR crossings between them. So they sort of turn a whole bunch of FPGAs into one glued together FPGA. But then the problem is, of course, how do you communicate between those different smaller, quote unquote, smaller, because these FPGAs are still very big FPGAs. And that's a problem that you get into with hardware acceleration. Like, you want to increase the frequency of your clock, which means you want your paths to be very close together so that the electricity has time to go from one part of your chip to the other part of the chip. If you're working with one specific crossing, there can only be so many signals that go across that crossing. And so that affects how fast you can clock your chip. And that's, yeah, that's a struggle that we've run into on other projects, but not on this one yet, because I am right now running it at low frequencies.
Okay, any final questions for Jonas before we wrap up?
I have another quick one. Any plans on moving to the FFT?
That's more what Michiel is doing right now. I would like to keep going on the NTT because I think there's a lot of things that can be improved. You can make NTTs a lot faster on FPGAs. FPGAs also have nice features for integer arithmetic, like they are very much built for integer arithmetic. there are some really nice things you, but yeah, without giving too much, like, for example, you have adder elements on the FPGA itself that work very well for splitting up your additions over one specific slice. I think these can go very well together with entities. So for now, I'm staying with entities because I feel like I feel like you can get more out of entities than out of entities.
There's still much to squeeze out performance-wise.
Yes,
for now.
for sure.
I see. Nice.
Okay, any more questions? All right, well, if not, Jonas, thank you very much for a very interesting talk. It was very informative and we had lots of engagement, which is fantastic. Everyone, I'm going to post the Discord link into the Zoom chat. So if anyone isn't already in the Discord, feel free to join, and I'm sure we can have some follow-up discussions there about this presentation. So yeah, thanks everyone for coming. All the resources will be uploaded as per usual onto YouTube and FHE.org within the week, so that everybody in the community can watch this talk. So yeah, until the next meetup, thank you everyone, and have a good weekend.
Thanks for coming.